On putting the load, so now we introduce a load. What will happen now is this. Okay, not that, sorry. Is this. The deformation is different. And this is still our load P. This is still our load P. So you can see the difference in terms of deformation pattern. Okay, you can see the difference in terms of deformation pattern. And if you were to ask me, Eugene, then if this is the case, what is the equation for deflection? Okay. So the equation for deflection changes. Is going to be y x, and is going to be equal to a term, and it's equal to C1 sine px plus by C2 cos px. Seen that equation before? Right? What type of rule? Imaginary. Remember? Right. Before we go on any further, okay, or I'll write out a few equations to bore you to death first. Okay. So the next thing that we're going to do is we are going to sketch again. Okay, I'm going to take the same diagram. Okay, I'm going to take the same diagram. Wait, wrong keyboard. Okay, I'm going to use the same diagram. And now I'm going to have a mathematical description on what is going on. Okay, so bear with me. So we know that this is A, which is our cross-sectional area. We have a load coming down, and this is coming down in P. I'll call this PX direction. Okay, I'm going to call this PX direction for now. Okay. And what we are going to have is the distance from here to here. This is L0. Okay. And I'm going to sketch for you. Okay. And I want you all to also get used to seeing what's going down here. If we draw this, this is known as built-in. Okay, this is known as built-in. So what will happen when it deflects? Okay, so on the right-hand side, we are going to draw the deformation pattern. Okay, ideal case, it means, make it in a sense that it's easy for us to analyze. So in an ideal case, right? So over here, I have an axis over here, which is our y-axis. And then over here, we have our x-axis. Okay. So when the structure deform, we are going to assume, okay, we make an assumption that it's going to be deforming this way. Okay. So this over here is a mathematical, description or describe, okay, how the structure will deflect. Okay, it's a mathematical description. Now, the next thing I'd like to introduce to you is if we are given where we have x, or we have x is equal to 0, right? We know that y is also equal to 0. So this case is our boundary condition number 1. And then we need to have our boundary condition number 2. And boundary condition number 2 states that when x is equal to L naught, y is also equal to 0. Okay. Why do we need the boundary condition? But if you look at our solution, y as a function of x, or we term complete inflection, we have a what? We have a second order differential equation that we have to solve with constant. So this is what the boundary condition is all about. Following from here, if we were to pick a point Q, okay, if we were to pick a point Q, and Q has relative distance, okay, so over here, this is our y, which represent our deflection. And the distance from here to here is a unique position at an x distance. Are you following me? Yes? Okay. So the next thing we're going to do is, like always, we have to construct a free body diagram. Okay, we have to construct a free body diagram. So we are going to next construct our free body diagram. Okay. So on our free body diagram, I'm going to have a green line. Let me make it thicker. Okay. And then on this green line, we have the load P, and then we have a deflection, and a deflection up to this point over here. This is our point Q. At the start of the point is where we have y is, or x is equal to 0. Y is equal to 0. Okay. So from here, we know, based on our free body diagram, we know that we have to have a what? We have to have a P prime, right? We have to have a P prime, and we need to have a counter moment. Okay? The counter moment is Q, or MQ. And we know why we need a counter moment, because it is under what? We have a certain distance over here, which is our y. Okay? So when you do your bending moment, what we classified this is what? Eccentric, symmetrical, bending. Does this ring a bell to all of you? Yes or no? You have eccentric symmetrical bending. So if we were to calculate our normal stresses in X, this will be equal to P over A plus or minus M. So if I were to MZ over IZZ multiplied by a distance, for example, I'll call this X. Sorry, it has to be Y. Does this look familiar? Okay, so we are in a situation now where we're bending, right? When we calculate a normal stress, is P over A plus or minus MZ over IZZ multiplied by Y. Okay? Right. So what we're going to do now is slightly different. So for buckling, okay, for buckling, we are going to take the moment. I don't think I need to draw anymore. So we're going to take the moment from where? From point Q. Okay, we're going to take. So everything anti-clockwise, summation of moment at point Q will be equal to 0. So Py is going in what direction? It's going in anti-clockwise direction, so it's positive. And this will be equal to minus moment at point Q is equal to 0. So therefore, moment at point Q is equal to Py. Now, I want you now to focus at point Q. So if we look at point Q, we have a load going up in P prime, and we have a moment coming down as MQ. Is MQ go clockwise or anti-clockwise direction? Clockwise or anti-clockwise? Clockwise. So therefore, MQ is equal to minus Py because it's going in the what? Clockwise. From here, we are going to apply the elastic curve equation to relate bending moment to deflection. Okay, if you guys have not done this yet, I don't think you guys have calculated any deflection yet. But take the formula as it is. Probably you guys have seen this in math. Okay. So what we have is Young's modulus multiplied by second moment of area d squared y over dx squared is equal to the moment. Okay. I look at you over there, try to stay over there. How rich is the cooking show and not? What are the difference between the two pieces of paper? One is longer than the other. Hopefully the density is the same. Right? Yes. What do we focus on moment? Right? That's what we try. If I put the stapler on top of the paper, can you imagine the deflection? No. So if I put it down, it is bending what way? This way. Exactly as what we have drawn before. Agree? Right? So how to prevent this? You have no choice. The paper is like that. Imagine. Because you cannot say you didn't buy bigger paper. No. It's okay. Right? You deflect this way. So the only way for us to prevent it on deflecting this way is to come up with a what? An axial load or a counter movement. Counter movement, yes, no. If we were to